Hello everyone, Mr. Linder here. Let's talk about decompression sickness as it relates to scuba diving. So the discussion on decompression sickness is interesting as it relates to the respiratory system because typically nitrogen does not have an effect on our human physiology unless you were to change the overall partial pressure of nitrogen gas. And the reason we're not concerned with nitrogen, even though it's at a high partial pressure within the atmosphere, if we take a look at the atmosphere and the levels of nitrogen, nitrogen actually makes up about 78% of our atmosphere. And yet, it has very little effect on human physiology because of its low solubility. Solubility constants were described by Henry, and it actually became known as Henry's laws. If you were to actually look at the solubility constant for nitrogen, so if we were to look at Henry's constant for nitrogen, it's about 1,600 liters atmosphere per mole. And that's in comparison to oxygen at about 770 and carbon dioxide at about 29 liters atmosphere per mole. What that basically means, if you were to do calculations using Henry's constants and looked at the solubility of these gases, actually carbon dioxide has the greatest solubility in water compared to oxygen. And both of those gases are greater in solubility than nitrogen. So what Henry's law allows us to calculate is what would the molar concentration in solution be at given partial pressures. And because the constant is so high for nitrogen at 1,600 liters atmospheres per mole, you get very little molar concentration in solution. So even though the partial pressure might be elevated for nitrogen, because the constant is so high, the molar values become very, very small when you calculate out how much is solubilized in water. What Henry's law shows, though, is that if you have an increase in partial pressure, so if the pressure increases, you can increase the molar concentration within a solution. So even though an inert gas like nitrogen, which is abundant in the atmosphere, and it will go in and out of our respiratory system as we're inhaling and exhaling, it's not soluble at sea level. There's very little solubility of nitrogen gas, so there's very little risk of nitrogen gas forming air bubbles in our circulatory system when we're talking about sea level partial pressures. But when you look at scuba diving and you're looking at increasing the pressure of gases, then that gas can become more and more soluble, because as the pressure goes up, looking at Henry's law calculations here, as the pressure goes up, the molar concentration within a solution will increase. So if the partial pressure of nitrogen, looking at Dalton's law of pressures, so if the overall pressure goes up, that means the partial pressure of the gas will go up. If the partial pressure of the gas increases, then the molar concentration will increase according to Henry's laws. So normally at sea level, we don't see nitrogen solubilizing in the blood, but during the event of scuba diving, there's going to be increased solubility of nitrogen in our blood because the pressure is going to increase when you're underwater. It turns out for every 10 meter of descent, so as we descend 10 meters underwater, there's going to be an increase of 1 atmosphere of pressure. And so as you increase 1 atmosphere of pressure every 10 meters, you're going to see more and more solubility of nitrogen within the cardiovascular system. And so this relates to scuba diving for two reasons. One, you're increasing pressure because you're underwater. And two, typically under normal dive situations, you are breathing a normal mixture of respiratory gases. So you're breathing in nitrogen and oxygen within your scuba diving tank. And so that nitrogen, according to Henry's law, is going to become more and more soluble the deeper you go in a dive. If you don't get that nitrogen out of your cardiovascular system, then that can lead to what we call decompression sickness. So diving compresses the gases and makes it more soluble within your cardiovascular system. And if you were to ascend too quickly and not blow that nitrogen off out of your system, that can lead to what we call decompression sickness or the bends. So let's take a look at this situation. So here we have a diver, and here we have our tanks that the divers are using. And of course, they're using a ventilator to get those gases into their cardiovascular system. If this was a typical dive, then we're talking about a mixture, right, of gases that are being brought into the respiratory system, and then those gases are going to solubilize into the cardiovascular system. So that mixture is going to be nitrogen and oxygen gas, just like you would be breathing at sea level or essentially above water as we breathe in regular atmosphere. Now, some dives are going to include other mixtures. There's helium that can be mixed within various tanks, but let's assume that we're talking about just a normal mixture of nitrogen and oxygen that you would typically breathe if you are not underwater. So scuba divers are breathing this nitrogen oxygen mixture as they descend underwater. As divers descend, the partial pressure of the gases, right, is going to increase. So the partial pressure of nitrogen increases during descent. Okay, so as the divers are going deeper underwater, the partial pressure, according to Dalton's law of partial pressures, that partial pressure is going to increase, and that's going to lead to nitrogen becoming more soluble in your blood because of Henry's law, right? So as if this is P equals HV times M, okay, as the partial pressure increases, we can see a direct relationship with the molar concentration of the gas within our blood. So we're seeing an increase of nitrogen solubilizing in our blood the further you descend underwater. So the amount of gas dissolving in the blood is going to be proportional to the partial pressure of that gas. If you are scuba diving and you're spending time underwater and you're increasing the amount of nitrogen that is in your circulatory system, you would want to make sure that you get that nitrogen out of your blood as you return to the surface. So as divers ascend, what you want to do is you want to off-gas, right, or out-gas the nitrogen. So you want to get that nitrogen out of your circulatory system because it's not normally supposed to be there. So as you ascend, you want to make sure that you ascend slowly, and you want to blow off, or you want to out-gas that nitrogen at regular intervals. And that's something that you would calculate prior to your descent. If you're going scuba diving and you're going to spend a certain amount of time underwater, you would calculate various stops where you would outgas the nitrogen from your circulatory system so that you don't suffer decompression sickness. The ascent rate, so typically when you ascend, returning back to the surface, ascent rate is typically about 10 meters per minute. And you're going to have these regular scheduled decompression stops so that you can outgas or blow off the nitrogen that is now solubilized in your blood because of that increased partial pressure of that gas. If you don't ascend properly, if you don't take regular breaks, that's where you have decompression sickness that comes into play. So if your ascent is too quick, you're going to have improper decompression, and that will lead to nitrogen bubbles forming within your circulatory system because nitrogen is not typically soluble within your blood. So instead of getting rid of the nitrogen gas, if this is your circulatory system, instead of off-gassing it because you ascend too quickly, that nitrogen begins to form bubbles of nitrogen gas, right, within your circulatory system. And those bubbles aren't typically there because typically nitrogen is not soluble at sea level pressures. But since you are underwater, you have this increased solubility of the nitrogen gas, and so that nitrogen is now circulating around within your blood. And then as you ascend, if you don't off-gas it, if you don't out-gas it at regular intervals, you're going to end up with bubbles in your circulatory system, and we call that decompression sickness. Decompression sickness leads to joint pain. It can also cause neurological symptoms, including seizures and paralysis. And it can also cause pulmonary symptoms like shortness of breath. And the joint pain is why many people call this the bends, because you double over in pain, you bend over in pain. And so this decompression sickness, or the bends, takes place. To treat decompression sickness would involve resolubilizing the nitrogen. So in order to resolubilize the nitrogen so that you can get it out of your body, you're going to have to go into a decompression chamber. So this device here is an example of a decompression chamber, and the decompression chamber is basically a device where you can change the pressure, and you can increase or decrease the pressure at the control panel. And so whoever is experiencing decompression sickness can enter into this chamber, and basically we can increase the pressure of the chamber. Okay. We can increase the pressure of the chamber. By increasing the pressure of the chamber while your patient is inside, you can resolubilize the gas. So you can take it out of those bubbles. So let's say we're looking at the patient's circulatory system, and they currently have bubbles of gases, of nitrogen gas. If you can increase the pressure, that gas will resolubilize. And so that it'll go back into solution. So rather than being an air bubble, it'll just be nitrogen in solution in the cardiovascular system, and it'll be circulating around just like any other gas within circulation. So increase the pressure, resolubilize the gas, get the air bubbles out of circulation, and then slowly return the pressure back to normal sea level pressure. So get it back to normal sea level pressure. 1 atmosphere of pressure is pretty typical. So get us back to normal 1 atmosphere of pressure over time, and allow for the patient to ventilate properly or breathe properly. So we want to ventilate properly. And while they're ventilating properly, you can blow off that nitrogen gas and get it out of your circulatory system, and therefore those bubbles won't form as you're heading back to normal 1 atmosphere of pressure. So we treat with this decompression chamber, up the pressure and then slowly decrease the pressure back to normal. We up the pressure to solubilize the gas, and then we reduce the pressure back to normal so that you can get the nitrogen out of the circulatory system and treat this decompression sickness that has occurred. Decompression sickness basically occurs when you leave a high pressure environment too quickly, and that solubilized nitrogen ends up forming bubbles in the circulatory system. So I hope you enjoyed decompression sickness and how to treat decompression sickness, and I hope that helps. Take care.